Hello students. Today we are going to start a session on modern physics. So modern physics in the JEE Mains paper usually comes around 4 to 5 questions that translates to 16 to 20 marks, and this topic is mostly formula based. So I would suggest that you guys work on this and you'll do better in your exams hopefully. So let us start from the beginning of modern physics. So the branch of modern physics started with the conception that light has a dual nature. What does this mean? So in the beginning, when Newton was doing his light experiments, he said that light behaves as a stream of particles. So if we draw a light ray, he said that it would have like a bunch of particles which are traveling along a straight line, and he called these particles corpuscles. So this theory was called Newton's corpuscle theory, and it could explain the then known light related phenomenon like reflection, refraction and total internal reflection and so on. But in the 1800s there was another experiment conducted. It was the Young's double slit experiment. So it had a light source, and in front of the light source there were a cardboard like this with two slits in it. And in front of this cardboard there was a screen. So if the light was a stream of particles like Newton suggested, the light source would emit particles. They would go through the slit, and we would see a bright spot here and we would see a bright spot here, right? But this is not the result of the experiment. The experiment showed us a interference pattern like this. So wherever I'm drawing the peaks, the peaks are showing the brightest points in the distribution. So this is the brightest point, followed by a little less bright point, and so on. So this could only happen if the light was a wave. So with this experiment, people started thinking that light was a wave. But then came Einstein's photoelectric effect. So the experiment was, he took a metal slab, and the metal slab had some free electrons in it, like usually metals do. And if on this slab you incident some photons are particles of light, by the way. So if you incident some photons, they eject the electrons, and these electrons can conduct electricity. So again, this theory can only be explained if the light is considered as particles. So with these major experiments in history, after this it was concluded that light has both wave nature and particle nature. And from Newton's photoelectric effect, he concluded a relationship. This relationship was energy of a photon particle, that is, this side of the equation shows the particle nature of light, will be equal to Planck's constant times the frequency of light. So this side is the wave part and this side is the particle part. So this relation combined the both natures of light, and hence we say that light has a dual nature. With this, as in I mean that we considering that light has a dual nature, next scientist, his name was de Broglie, but his spelling is de Broglie. But we don't spell it as de Broglie, we call it de Broglie. So this scientist de Broglie said that if light has dual nature, matter should also have dual nature. It means that matter around us, like my sketch pen or an electron or anything, will also behave as a particle and wave simultaneously. But don't you think it is a bit absurd to consider this sketch pen a wave? So what he proposed was the wavelength of matter particles is given by Planck's constant divided by momentum of the particle. So I can rewrite this as Planck's constant by mv. Now for this sketch pen, the mass is quite high, which means the wavelength will be quite low. So if you consider a very small wavelength like this, it could almost be approximated as a straight line. Therefore we can see, you could visualize that if I throw this sketch pen, it would travel in a straight line, not in a wave. That is how you explain the large size particles behaving in a straight line. So this relation can also very easily be proven. Consider this. Consider the Einstein energy relation, E is equal to mc squared. From this you can write m is equal to E by c squared, and from Einstein's equation you could write energy as hc by lambda into 1 by c square, right? Now cancelling out c's, you get h by lambda c is equal to m, and transposing this, lambda is equal to h by mc. So m is mass of the particle and c is speed of light. So you could combine this and write this as momentum. So lambda is equal to Planck's constant divided by momentum. This was de Broglie's relation. Now let us simplify this relation a bit further. So you could write momentum as root of 2 kinetic energy times mass, right? You write the formula of kinetic energy and simplify this, you'll come here. So if we substitute here, lambda of a particle can be given by Planck's constant divided by root of 2 kinetic energy by mass. Now if you apply this relation to a single particle, let's consider an electron. So for an electron, we know that Planck's constant is a constant, obviously. 2 is a constant, and we know the mass of electron. So if you plug all the values in this equation, you land up with lambda of an electron, that is wavelength of an electron, will be given by 150 divided by kinetic energy square root. So this kinetic energy is in electron volts. So if you put in the kinetic energy of an electron in this equation, you will get the wavelength of that electron. So this is how we can show that an electron can be considered as a wave, and expanding the same relationship, an electron, which means all matter, can be considered as a wave and a particle both. Now let us move on. This was the de Broglie's analysis. This was the de Broglie's hypothesis. To prove this hypothesis, an experiment was conducted. I would highly suggest you to go look up that experiment in your free time, because a very similar experiment to Young's double slit experiment, a source of electrons was placed and a mesh was placed in front of it and a screen. So the problem in this experiment is, how do you let a very small stream of electrons through a slit? So it was solved in a very interesting way. If you have time, you can go check this experiment out. So after the conclusive proof of this experiment, it was de Broglie got his Nobel Prize for his theory, and taking inspiration from de Broglie's theory, another scientist whose name was Niels Bohr, what Niels Bohr did was he considered that electrons are waves. So from that he could say that, so there was a problem existing in the earlier atomic models, right? The Rutherford atomic model. So its problem was, if there is a nucleus in the center and a negative charge is revolving around the nucleus, classical physics tells us that the negative charge should get attracted to the positive charge and collapse in the nucleus. But this doesn't happen. So what Niels Bohr did was, he told us that the negative charges revolve around the positive charge in set orbits, and these orbits have their own specific energy levels, which it means that the electron revolving in this orbit, like let's call it 1, will have some certain energy level, and if it has to move from this orbit, let's say it has to go to the higher orbit or a lower orbit, it will have to be given the exact energy level, the exact energy that is the difference between these two levels. So let's say that this electron wanted to go to a higher level, let's call it 2. It will have to be given energy that is equal to energy of the first shell minus energy of the second shell. So if this is the case, like the electron could make transition only if this amount of energy was supplied, nothing less and nothing more. And he further proposed that each of the shells have a specific energy level and they are quantized. Like the angular momentum of these electrons in the orbits is given by mass, like angular momentum is given by mvr, and this mvr is quantized. You could say that it is an integral multiple, like multiple of h by 2 pi. what do I mean by integral multiple? So it cannot be a fraction of this. It always has to be an integer multiple. Let's put an integer n. So this n has to always be an integer. It cannot be a fraction, which means that electrons cannot jump in between here or here or here. They always will jump between the levels. And this n is called the primary orbit number. So let us say that this is the relation first from the Niels Bohr's theory, and now let us apply Newton's relation to this system. A negative charge revolving around a positive body at a, let's call this distance as Rn, that is the radius of the nth orbital. So let's call this Rn. So from Newton's second law, we get that the centripetal force that is keeping the electron in motion will be given by mv square by r n. So this would also be Rn, is equal to the force of the electric attraction between these two, that is given by 1 by 4 pi epsilon naught E square by Rn square. Let us call this equation 2. So if we solve these equations simultaneously, like then we would get the values of Rn and V. The relation for Rn is given by epsilon naught n square h square divided by pi m e square. Don't worry, you don't have to derive these relations. You don't even have to remember the whole relation. We'll get to a simpler form. You can keep that in mind. So epsilon naught is a constant, Planck's constant is a constant, pi is a constant, mass of electron is known, charge of an electron is known, everything except for n square is known. So if we put values of everything in this relation, we will get Rn is equal to a constant value, that is 0.529 into 10 raised to minus 10 into n square. Or we could also say Rn is proportional to n squared. And similarly with velocity, the relation for velocity in the nth shell is given by E square by 2 epsilon naught n into h. Now again all of them are constants except for n, and from this relation we get 2.19 into 10 raised to 6 divided by n, or we could say V is proportional to 1 by n. So Bohr's theory tells us that the electrons, the radius of electron is the radius of an orbital is proportional to the square of the orbit number, and velocity is inversely proportional to the orbit number. So as we go further from the nucleus, the velocity decreases and so on. So this was Bohr's theory. So taking this further, there is one interesting thing that happens here. So as we discussed earlier, let us say this is a nucleus and these are the orbit numbers around the nucleus. What happens is, if an electron is given some energy, not some energy, the exact energy between these two, it will make a transition from a lower orbit to a higher orbit. But since this is not its stable state, it has gained some external energy, it does not stay here. It will again emit this energy and try to go back to its ground state. While doing so, it will again emit energy that is exactly equal to the difference of these energies. And that for any given atom is like this energy that is coming out of electron jumps for any given atom. Let's say for example a hydrogen atom will have a very specific sets of wavelengths that emit out when energy is supplied to the hydrogen atom. Hydrogen atom will give out a specific set of wavelengths that it gives out when its electrons jumps from higher energy level to lower energy level, and that we call as an emission spectrum. So this emission spectrum is unique for a hydrogen atom, a helium atom, a lithium atom, and so on. What it means is, if you excite a hydrogen atom, it will give out some radiations and those will be unique to hydrogen atom. So you could say it is a fingerprint of sorts. So this is the way in which we investigate the composition of faraway stars. So let's say a light from a star is incident on Earth. You could collect all the wavelengths in that light and you could know what elements make up that star. So that was about emission spectrum. There's one more thing about emission spectrum. Like earlier we discussed that light is emitted whenever electron makes a jump from higher orbit number to a lower orbit number. So let me draw a diagram for you. Let us call this energy level 1. This is the second level. This is the third level, fourth, fifth, and so on. Like at max you can consider 7. So let's draw them, 6 and 7. So one thing I want you to notice is I progressively reduce the distance between the energy levels, and this is another finding of Bohr's theory, that energy of any orbital is given by minus 13.6 by n square electron volt. Electron volt is the energy unit we use at such smaller levels because this is a very small unit. So what this minus signifies is you have to give 13.6 electron volts of energy to an electron that is in the first orbital to make it free of the nucleus. So negative signifies energy to be given to the system. So now coming back to the our problem. So the energy is inversely proportional to n square. So as n goes on increasing, the energy goes on decreasing in square relations. So the difference between the first two will be large, and it will successively go on decreasing. That is why I have drawn the first two far away and the next ones closer to each other. So whenever an electron makes a jump from 7 to the first, it will emit energy that is equal to the energy difference between 7 and the first. So similarly this happens for the 6th level, 5th level, 4th level, 3rd level and 2nd level. So all the electron jumps that end up at the first energy level are called Lyman series. Let me repeat this one more time. Whatever electrons jump to the first level, like let us say an electron starts from the 3rd level and jumps to the 1st level, it will fall under the Lyman series. So Lyman series is the name given to all the electron jumps that end up on the 1st level. Very similarly, all the electron jumps that end up to the 2nd level are called Balmer series. So these are named after the scientists that discovered these series. The third one is called Brackett series. The next is Paschen series. And the last one is Pfund. So it's Fund, don't pronounce the P, it's Fund series. Okay. Now, the light that is emitted in each of these series, since the energy levels are different, the light wavelengths will also be different. So Lyman series light wavelengths fall in the ultraviolet range. Only Balmer series falls in the visible range, and Brackett, Paschen and Fund, all of these three fall in the infrared range. Okay, so now let us look at the formula that gives us the that will give us the wavelength of the photon that is emitted when an electron makes a jump. So the formula is given by 1 by lambda. That is, this lambda is the wavelength of the photon that is emitted by an electron jump, is given by minus r. This is the Rydberg constant into 1 by n final square minus 1 by n initial square. So these n is again the primary orbit number. And if we multiply both sides by hc, we will get hc by lambda. That can be written as energy. So energy is equal to minus r hc bracket में 1 by nf square minus 1 by ni square. So this is another important relation. This relation gives us the energy of the photons that jumped from higher to lower levels or lower to higher levels. Then in that case we'll get the energy that is required for the jump. This was the Bohr's theory. Page. Now there's one important drawback of the Bohr's theory. That is, the Bohr's theory tells us that if there's a nucleus, then there are set paths in which electrons rotate, right? Which means that you could exactly locate an electron in this path. But there's another theory, which is another founding theory of modern physics. It is Heisenberg-Uncertainty. So what Heisenberg-Uncertainty tells us, that you can never ever find the exact position of an particle and its exact momentum at any given instant. So what it means is, let us say that delta x is the uncertainty in the position of a particle, multiplied by delta p is the uncertainty in its momentum. This will always be greater than or equal to h cross by 2. So h cross is Planck's constant divided by 2 pi and divided by 2. So it can never ever be 0. It always has to be greater than this constant. So if you find very accurately, like in Bohr's theory, you could say that electrons revolve in this orbit, which means delta x will tend to 0. In that case, delta p will be very, very high to keep this relation. So you can never ever know where the electrons are exactly placed or what their momentum is. All you can actually say is electrons can be found in this region somewhere. So then this changes from a deterministic model, that is, you could determine the position, to a probabilistic model. So you can probably say that this is the region where the electron is most probable to be found. So this was the Heisenberg uncertainty principle. So these are the major topics that we had to learn today. Let us solve a question regarding whatever we learnt. So let us look at this question. So let me read out the question, then I'll explain it to you. An electron from various excited states of hydrogen atom emit radiation to come to ground state. Let lambda n and lambda g be the de Broglie wavelength of the electron in the n state and the ground state respectively. Let I don't know what this symbol is called. I'm just going to call it an. An be the wavelength of emitted photon, and in the transition from the n state to the ground state, and for a large value of n and a and b being constants, we have to find which of these relation holds true. This question had come in IIT mains exam in the year 2018. So I picked this because it would cover everything that we've learned today. So the question says that there's a hydrogen atom, and the electron of a hydrogen atom jumps from the nth orbit to the ground orbit. So ground orbit is used for the hydrogen atom. Ground orbit would be 1. So let's call it the first orbit. So it does this jump, and the wavelength, de Broglie wavelength at nth orbital was lambda n, and the first is lambda g. Okay, and in this transition it releases some energy, and that energy is given by, so this symbol is called tilde, by the way, tilde n. This wavelength is given by tilde n, and what we have to find is, we have to find the relation between tilde n and lambda n. Okay, so now, just right now we had seen the energy distribution, energy of the photon that jumps from a higher level to a lower level. Let me write that relation for you. So the energy emitted by a photon from nth level is given by minus r h c 1 by ni square, nf square minus 1 by ni square. Correct? Now in this, for En we can write lambda n divided by, we can write Planck's constant into C divided by lambda n, and that is equal to the same things. So Hc and Hc will get cancelled out, and we are left with 1 by lambda n is equal to minus r. Now the final nf would represent the final orbit number where it jumped to, that is the ground state. In our case, the ground state is given by 1. So this becomes 1 by 1 square minus the initial the initial orbit number from where it had jumped. So that would be 1 by n square, correct? Now let us simplify this a bit. 1 by lambda n will be equal to minus r into 1 minus 1 by n square. Okay. Now let us take the de Broglie wavelength relation. The de Broglie wavelength relation tells us that lambda n is given by h by momentum, that is mv. Now from this I want the value of m. So why that is, I'll tell you soon. M is equal to h by lambda n divided by velocity. Now let us keep this as it is. And from the Bohr's atomic model, we get that angular momentum of an atom is mvr. mvr is equal to nh by 2 pi. So in this relation I wanted to substitute m. That is why I got m's relation here. So if I substitute, what I get is h by lambda n into v is into vr is equal to nh by 2 pi. On simplifying, h gets cancelled out, v gets cancelled out, r will go to this side and lambda will go to so 2 pi will come here. So 2 pi r divided by lambda n is equal to n. Now in this, 2 is constant, pi is constant, lambda n we have to keep, and n and r are variables. So we need to either eliminate r or n. So do you remember in the beginning when we saw Bohr's theory, we related the radius of an orbital to its orbit number. So Rn is equal to some constant that we found out earlier, let's call it c, into n squared, correct? So I'm going to put this here, which gives me, like I'm substituting r here, which gives me 2 pi c n square divided by lambda n is equal to n. Square and n cancels out, lambda goes to that side, so lambda n is equal to 2 pi c, some constant c, into n. So I can say that lambda n will be equal to, I'm calling this whole thing as some other constant b into n. Okay, now I can put this in this relation. So I have a relation between n and lambda n. So I'm going to substitute it here, which gives me 1 by, so this would be the wavelength of the emitted photon, that is tilde, not lambda. This is tilde n. So 1 by tilde n will be equal to minus r by 1 minus 1 upon n square. I'm replacing by 1 upon b. I'm calling 1 upon b some other constant. We could say that let's say c dash into lambda n square. Now if we reverse this, we will get tilde n is equal to 1 by minus r into 1 minus 1 upon c dash square lambda n square raised to minus 1. Now if n is a large number, it means that lambda would be less, which in turn tells us that if lambda is less, the whole fraction is much lesser. Sorry, if n is greater, this is a direct relation, if n is greater, lambda n will also be greater, which means if denominator of a greater number square will be even greater, making this fraction a very small number. Now expanding this as a binomial theorem, if we expand this, we get 1 by minus r is equal to 1 plus 1 by c dash square lambda n square. And all the other terms in the expansion can be neglected because this is again a very large number, and the higher powers of larger numbers in the denominator will go closer and closer to 0. So you can ignore whatever is left. So finally we could say tilde n is equal to, multiplying this inside, I will get some constant, because r is a constant, I'm saying that some constant a, plus multiplying this inside 1 by minus 1 by r upon some constant, that is again I'm considering 1 by r into whatever this is, another constant b, divided by lambda n square. So this is the relation between the wavelength of the emitted photon and the de Broglie wavelength, and this will be the option number 2. That is how you prove the this is how you solve the question. So the further my colleague will take you to modern physics part 2, and this is where we part.
Should I write with this one? Yeah. Okay, the questions are here. Okay, fine. Okay. Now it is okay. So, the mic audible?
Yeah. You can start.
Will you start?
You can see those purple marks there.
Okay. It's fine.
You can see those purple marks there.
But it's difficult to know. I mean, write like this. Should I start? Hello students, good evening. We were discussing on modern physics. So in the previous class, we have, your sir have already discussed on photoelectric effect. He hasn't discussed, he just mentioned that. So I'll start from there. Now, before moving on to photoelectric effect, we need to understand something called electron emission. From the first part, you have understood that when waves, every particle has a dual nature. It can have a wave nature as well as particle nature. So when one particle bombards another particle, the particle can move away or shift away. Now when, in the case of electron emission, electrons, free electrons, they move within the boundary of the metals. But in some cases, they can fly away from the metal if these electrons have sufficient energy. Now, how are the ways the electrons can fly away? There are 4 number of ways. First is thermionic emission. That is when thermal energy, normal heat energy is provided, sufficient heat energy is provided, electrons can emit from the metal surface. Second is field emission. Electric field, it can emit the electrons from the metal surface. 3. Secondary emission. high-speed electrons or other particles from other metal bodies moving. It can also emit the electrons. And finally, we have the photoelectric emission. That is, by the word photo, you know, photo means light. So when light energy of sufficient energy hits a metal surface, if this light energy is sufficient enough to knock off the electron, it can knock off the electron. Now, what do I mean by the word sufficient enough? Every metal surface or every material, they have a minimum energy. It needs a minimum energy to knock off the electron, and that is called the work function. It is denoted by phi 0. Okay. Now, when the minimum energy that a metal surface requires is called the work function. Now, the four ways that we have discussed already, with all the four ways, this minimum energy needs to be provided. Now, when we are talking about light, that is photoelectric emission, light should provide that minimum energy. Light should provide the minimum energy. Now, suppose the energy of incident radiation is EI. You have already studied from the modern physics part 1 that energy of an incident radiation can be written as Planck's constant times the frequency of the wavelength. Now, it is h into nu, so EI equals to h nu. Now, if this energy is greater than the work function, then only the electrons within the material will have energy to absorb and be emitted. Now, so the minimum energy that we are providing is phi 0. That is the work function. So we can write phi 0 equals to h nu 0. Now, what is nu 0? Nu 0 is called the threshold frequency. Nu 0 is the threshold frequency. Now, therefore, if EI is the incident energy and phi 0 is the work function, then the remaining energy should be utilized to provide the energy, to provide the kinetic energy of the emitted electrons. So we can write that h nu is the energy provided of the photon will be minus phi 0 equals to kinetic energy, maximum kinetic energy of the emitted electrons. That is h nu equals to phi 0 plus kinetic energy. And we can write h nu, phi 0 is nothing but h nu 0 plus half mv square maximum. Now, what is mv square maximum? V maximum is the maximum velocity an electron has. So h nu is the energy given by the photon. H nu 0 is the work function, where nu 0 is the threshold frequency. plus the remaining amount of energy is nothing but the kinetic energy of the emitted electrons. This equation we will use basically to solve our problems in photoelectric emission. Now, we can modify this equation in terms of wavelength. We have written h nu equals to h nu 0 plus maximum kinetic energy. Now, you know that wavelength equals to the speed by frequency. So definitely we can write h c in place of frequency we can write c by lambda. So h c by lambda equals to h c by lambda 0 plus kinetic energy. So in terms of wavelength, you can see the work function is h c by lambda 0. So the wavelength is in the denominator. So there can be a maximum limit of the wavelength. Beyond that, if wavelength is greater than lambda 0, the energy of the photon will be less than the work function. So when the wavelength is greater than the threshold wavelength, the photons will not be able to emit electrons. So in case of threshold frequency or the frequency of the electrons should be always more than the threshold frequency, whereas in the case of wavelength it should be always less than equal to the threshold wavelength. Whatever be the case, we will be using these equations for our solving of our problems. Okay, next we'll come to another concept called the stopping potential. Okay, we were talking about emission of electrons. One simple experiment was conducted with the emission of electrons. It was like yes, there were two plates P and Q. P is positive, Q is negative. We are applying a voltage V across it. Well, V is variable. Now, incident photons are incident on the plate P. Now, what is happening? H nu. H nu is the frequency of the incident photon, when nu is the frequency of the photon. And P and this metal plate is having the work function phi 0, which is h nu 0. Now, when photon is incident on the plate P, electrons were emitted. They are having the kinetic energy which is equals to h nu minus phi 0, which is nothing but h nu minus h nu 0. Now see, electrons have emitted, but Q is at a negative potential. So what is the normal tendency of the electrons? The electrons will be repelled, but as electrons, they do have a kinetic energy. Few electrons can cross this distance and can fall on the plate Q, and finally they can complete the circuit. So if you place a galvanometer in this, we will see a deflection in the galvanometer. So when the electrons are moving through this, the galvanometer will show some deflection. So it means because of these photons, the electrons, they are forming a photoelectric current. But suppose we go on increasing this voltage. if we go on increasing this voltage, then what will happen? The repulsive force is increasing. As a repulsive force is increasing, less number of electrons are now falling on plate Q, and slowly the deflection of the galvanometer will be decreasing. At a particular point, at a particular voltage V0, we will see no electron will be able to fall on Q. So no electron will be having that kinetic energy to cover up this repulsive force, and so we will be not having any photoelectric current. So photoelectric current will stop, and hence this voltage is known as the stopping potential. Now see, this part, I mean this volt is negative to this. This is minus V0. So, and we know the work done is nothing but charge into voltage. The charge of one electron is minus E V0. So we can say the work done on the electron is minus E V0. And that negative work done is actually responsible for decrease of the kinetic energy. Now you know the work energy theorem. Work energy theorem says what? The work done is equivalent to the difference of kinetic energy, final and the initial. The final kinetic energy is 0, and what is the initial kinetic energy? It is the maximum kinetic energy, that is Ke. So we can say this maximum kinetic energy Ke is nothing but, so maximum kinetic energy Ke is equals to h nu minus h nu 0. So or equals to, I can say the maximum kinetic energy can be, it is half. So I can write, instead of maximum kinetic energy, yes, we can place it to be as EV0. EV0 equals to h nu minus h nu equals to h nu 0 plus phi 0. Stop. Just गड़बड़ हो रही है यहाँ पे. You can take a pause. यहाँ पे क्या मैं गलत. Wait. I'll start once again. That's fine. Yes, the maximum kinetic energy is nothing but half mv square max, which we are denoting by EV0. So we can say the maximum kinetic energy is nothing but related with our stopping potential, and we have seen Ke max equals to h nu minus the work function. So we can write EV0 equals to h nu minus our work function. So the stopping potential V0 is a function of the frequency. So if we divide V0 h nu by E minus phi 0 by E, we'll all use this equation for our problems. Let us see how we can relate photoelectric emission with graphs. Now what we saw when light of frequency nu falls on a metal surface, electrons are emitted. Now, how does the frequency of the light nu affects the emission of electrons? If you remember the previous problem and the previous experiment, now what we do, this is P and this is Q, this is the galvanometer G. We have placed the voltage such that Q is at positive potential. So now when the electrons will be emitted, it will be accelerated towards Q. It will be accelerated towards Q. Now if you see that, so what will happen, it will go on. So it did have a stopping potential. From the stopping potential, if you have increased slowly the electron current will increase. Finally it will be a saturated current. Why? Because when all the electrons have sufficient energy, it will come to this plate and the current will be saturated. So no more electrons are there to complete the circuit. So the current will be saturated. Now, suppose we increase the intensity of light. If we increase the intensity of light, what does this mean? That number of intensity is dependent on number of photons falling per unit surface area So when number of photons falling per unit surface area is increasing, then chances are more number of electrons will be increasing also. So definitely if more number of electrons are increasing, when more number of electrons are increasing, then what will happen? The current will also increase. So if this is the intensity I, if this is the intensity, if it is double intensity, what we can see that the current has increased because of this intensity. But see the stopping potential remains the same because we haven't increased the frequency of light. Frequency of light is kept constant because h nu, this energy is responsible for the maximum kinetic energy. So when h nu is constant, when nu is constant, h is a constant, maximum kinetic energy remains same. So stopping potential, which is related with the maximum kinetic energy, it also does not change. But now if we use two lights of two different frequency, suppose for this and of the same intensity, we will see for the first one, if the stopping potential is V01, for the next one, if we see nu2 is greater than nu1, then definitely E2 will be greater than E1. Its saturation current will be same, but its stopping potential will be more. Stopping potential will be in the negative direction. The stopping potential will be more because higher frequency means higher energy. Higher energy means the stopping potential will be more. Okay. Now these are the two very important graphs we use for the problem solving. Now we'll draw a few other graphs. We have seen that the Ke maximum equals to h nu minus the work function phi 0. Now we'll try to draw a graph between the maximum kinetic energy and the frequency. If you compare this graph with normal straight line graph y equal to mx plus c, you can see frequency x is the x and k max is the y, where h is the slope and minus phi 0, that is the y-intercept. So if you draw the graph between frequency and, we will see the graph forms a straight line where this will give, this slope gives h and this is nothing but minus phi 0. If we take a different material whose work function is different, we can see this is minus phi 01, this is minus phi 02. The slope remains the same, but the work function is different. Now we have also derived previously that by dividing this k max is nothing but EV0 equals to h nu 0 minus phi 0. Then V0 equals to h nu 0 by E minus phi 0 by E. Now if we want to plot, sorry, this is nu versus this, we will see two graphs where this will be minus phi 01 by E, this will be minus phi 02 by E, and the slope of the graph will be h by E. So in both the cases, the maximum kinetic energy with respect to frequency and stopping potential with respect to frequency, it will be a straight line just with two different slopes. But in the same graph, the slopes are not changing. What is changing is the intercept. Okay, this comes to the equation of the photoelectric current, photoelectric theory. Let us see how we can solve some problems. Okay. The first problem, the first two problems are very simple, very straightforward. First question. For photoelectric emission from certain metal, the cutoff frequency is nu. If radiation of frequency 2 nu impinges on the metal plate, the maximum possible velocity of the emitted electron will be. See, it is a very straightforward question. Let us see what we can do with it. For a photoelectric emission from certain metal, the cutoff frequency is nu. So means the work function is definitely h nu. If radiation of frequency 2 nu impinges on the metal plate, the maximum possible velocity of the emitted electron will be. Now we know the maximum kinetic energy is nothing but energy of incidence minus the work function. Now for the energy of incidence, the frequency impinges is 2 nu. So it is nothing but 2h nu, and the work function is h nu. That is h nu. Now Ke max is nothing but half m into maximum velocity square equals to h nu. Therefore V is nothing but 2h nu by m root. This is a very simple and a straightforward question. Let's go on to the second question. When the energy of the incident radiation is increased by 20%, the kinetic energy of photoelectrons emitted from a metal surface increased from 0.5 electron volt to 0.8 electron volt. So when the energy of the incident radiation is increased by 20%, the kinetic energy of the photoelectrons emitted from a metal surface increased from 0.5 electron volt to 0.8 electron volt. The work function of the metal is. How to solve this? Same equation, same problem. Now initially the energy, the kinetic energy equals to energy incident minus the work function. Now First, initially the kinetic energy is 0.5 electron volt. Energy is EI minus phi 0. This is first equation. Second equation, energy is 0.8 electron volt. Kinetic, the energy of incidence is 1.2 EI minus phi 0, 2. Now these are two simultaneous equations where are two unknowns. Now what we can do, we have to find phi 0. We can just do like this. We can write EI equals to 0.5 plus phi 0, whereas 1.2 EI will be equals to 0.8 plus phi 0. Now if you divide this by this, EI will cancel out. It will be 1.1.2 will be 0.5 plus phi 0. I am not proceeding further. If you solve this, we can easily find out the work function. These kind of easy problems come in the joint entrance examination. Now, let us go into more complex problems. This is also a straightforward question on graphs. Intensity and frequency of incident light both are doubled. Intensity and frequency of incident light both are doubled. Then what is the effect on stopping potential and saturation current? So it is a very straightforward question. If frequency is doubled, stopping potential will also be doubled, because we have seen, because intensity and the frequency, stopping potential so if frequency is doubled, stopping potential will also be the, and what about the intensity? Now when intensity is doubled, we have also seen, if the graph is like this, if frequency is doubled, stopping potential is doubled also, and intensity doubling means more photons, double number of photons is now incident on the plate, and hence we cannot say it will be doubled, but chances of electrons being emitted is more than previously. So intensity, if it is doubled, the saturation current will increase, but we cannot say it is doubled. So this kind of question is on graph. Let's move on. Okay. This is a very important question. It came in JEE 2016. In a historical experiment to determine Planck's constant, a metal surface was irradiated with light of different wavelength. The emitted photoelectron energies are measured by applying a stopping potential. The relevant data for the wavelength of incident light and the corresponding stopping potential are given by this. Now, c speed of light and electron charge is given. We have to find the Planck's constant. Let us try to analyze the question. A metal surface was irradiated with light of different wavelength. Here, the key point is different wavelength. So we can write stopping potential so we also know the stopping potential. Stopping potential is nothing but the maximum kinetic energy. Sorry, this will be the maximum kinetic energy. The maximum kinetic energy we can change EV0. Now great. So this is the stopping potential are given. Now this is constant. This we can write phi 0 plus EV0. Now there are two values. Lambda is in micrometer, V0 is the stopping potential. So we can write for the first value, lambda is 0.3. Mind, it is in micrometer. This is phi 0 plus 2e. Second, hc, it is phi 0 plus e. Now these are two equations. If we subtract equation 2 from 1, we will get hc 0.3, that is phi 0 cancels out, it becomes E. Now we have to find out the value of H. Now we'll proceed. H, C, this can be solved to, this can be written as 10 by 3 minus 10 by 4. And mind, these are in micrometers. So if we write this is 10 to the power 6 equals to E. So find, so H, C into 10, this is 1 by 12 into 10 to the power 6 equals to E. Now this becomes 5, 6. So H equals to E by C into 6 by 5 10 to the power of 6. E is 1.6 into 10 to the power minus 19. C is 3 into 10 to the power of 8 into 6 by 5 and multiplied by 10 to the power of minus 6. If you calculate now, this 3, this becomes 2, 1.6 into 2, that is 3.2. 3.2 divided by 5 is 0.64. 0.64 into 10 to the power minus 19, this is 10 to the power 8, 10 into 10 to the power minus 6, that is 10 to the power minus 25, 10 to the power minus 25 and minus 8, 10 to the power of minus 33. That it becomes 6.4 into 10 to the power minus 34 joule second. So if you look at the answer will be 6.4 in the minus 34 joule second. So these kind of problems usually you will get in JEE. Only one question comes usually from the photoelectric effect, and just by using the basic formula, that is maximum kinetic energy is equal to the energy incident minus the work function, and if you can write the equation in terms of threshold frequency or threshold wavelength or in terms of stopping potential, and also knowing the graphs, you can solve most of the questions, all the questions of photoelectric effect. Thank you. Thank you.